Okay.
Can I get a drink real quick? Is that
Okay, Pastor.
okay? Okay.
I do not see Sally. Otherwise, we're here. First, a note about the homework. Problem 4. I did the problem, but I didn't bother about putting numbers in because what could go wrong at that point, right? Yeah. They had 2 mistakes in their answers. Mistake number 1 was the diameter said it was a diameter of like 0.2 centimeters, which when you think about it is really stupid. It was supposed to be 2 meters, or 0.2 meters. But they wrote 0.2 centimeters. They did their solution as if it was 0.2 meters. Right? If it was a 0.2 centimeter, that means it's, this big. You're not collecting too much light with something that big. Right? So it would be kind of stupid. But that was their first mistake. Their second mistake was that they took the specific heat for water and the specific heat for aluminum, and they flipped them. So, for instance, in Michael did his correctly, and it said, make sure you have the specific heat for aluminum, specific heat for water correct. Well, he did have them correct, but they didn't. So I went through and I regraded them by hand. So the grades that are there show, what you have. So we have people like Reagan showing great confidence. He just put in the correct answer and went on. Most people, they put in an answer, it tells them they're wrong. They're like, oh no, and try to figure it out. He just had that confidence. It's got to be right. Okay, so I want to make sure we're clear on that. The exam is tomorrow in lab. For class on Wednesday, make sure you've completed Concept Coach for all of Chapter 28. But for today, we're going to look at what's going to be on the exam during the lab. So for the exam, we're covering chapters 25, 26, and 27. I've gone through and renamed the chapter reviews, so that they match better the chapters in our current textbook, since the questions come from a different textbook.
Match better or match exactly? Like it is 25, 26, and 27 now?
Well, they say one says 24 and 27 because the chapters are divided up, content's divided up differently in different textbooks. Okay, so chapter 25, geometric optics. Geometric optics was where we treat light as if it is traveling as a ray. So make sure you understand why it makes sense to treat light as a ray. And then we have Huygens principle, which I hope I spelled right. I didn't look it up or anything. Huygens principle that says each point on a wavefront can be treated as a new point source of light. Huygens principle can then be used to say light travels in a straight path as a ray. The original observations come from, we looked at light and it appeared to do that. But Huygens principle then allows us to see, if Huygens principle is right, then the light should travel as a ray. And when light hits a mirror and reflects, make sure you know about not just specular reflection, but also about diffuse reflection. Specular. Specular reflection is mirror-like reflection. Reflections that occur when light hits a very smooth surface. The diffuse reflection is the reflection when light hits a rough surface. Because it's a rough surface, instead of having a nice, neat pattern of reflection, it's reflected in all different directions because the surfaces are all different directions. So make sure you can identify the difference. Which one did we use for all of our optical work? We use the specular for all of our optical work, right? We make mirrors, and those mirrors have specular reflections, not diffuse reflections. But when I look at the colors on Chad's shirt, I'm looking at diffuse reflection there. Or when I look at your face or your hair, or anything else where I'm not seeing what I see as a reflection, but when I think I'm seeing the object, then I'm looking at a reflection, but it is a diffuse reflection. Refraction. Refraction is governed by Snell's law. So make sure you know how to calculate an index of refraction. And simple things like when you go into a medium with a higher index of refraction, the light refracts toward the normal to the surface. When you go into a medium with a lower index refraction, it refracts away from the normal to the surface. If it refracts away from the normal, that means your angle of refraction is bigger than your angle of incidence, and you could get to a situation where it might predict your angle of refraction is 90 degrees. If your angle of refraction is 90 degrees, that means your refracted light is parallel to the interface between the two materials. It doesn't get out. And so when you reach that point, we call that the critical angle, and then you have total internal reflection. So make sure you understand why total internal reflection occurs, how to calculate it. Remember, for total internal reflection, theta 2 is equal to 90 degrees at theta critical, at the angle where you start to have total internal reflection. That's how we define it when you get to that 90-degree refraction angle. Make sure that you can describe how a rainbow is made, the geometry. Remember, you had the first order bow. That's first order. And the second order bow okay, my pictures are kind of quick and dirty here, but you understand there's one reflection in the first order bow, two reflections in the second order bow, and there's one crossover because of one reflection in the first order bow. There are two crossovers because of two reflections in the second order bow, and those crossovers invert the order of the colors. So that's why the order of the colors in the first order bow is inverted from the order of the colors in the second order bow, because an additional reflection causes an additional crossover. And of course, why are the colors separated at all? Different wavelengths have different speeds of light in water, and hence different indices of refraction. So you have different colors refracted by different amounts. And in this picture, let's call these, I don't want to call them anything that's in an order. Or if I call them in an order, then it biases things. Which one of these is going to be at the center of the rainbow? This one here or this one here? Okay, I had an answer at the bottom. Consensus? Another top one. Well, it has to be one of those two. And it turns out that it is. That it is one of those two. This one here is what's going to be on the bottom of the bow, and this one on the top of the bow. How do I know that? Because this is steeper. This one's flatter. So the flatter angle I'm going to see at a lower, steeper angle I'm going to see at a higher. Yeah, I believe that it's red here. Okay, that's not red. We'll just put blue here. Change to red. So I remember right, red's at the center, right?
No, red's in the top.
Red's in the top? Ah, crud. See how well I know my colors of the rainbow? My sister found it just boggling that people didn't have this memorized, and I'm like, yeah, crazy people. Okay. So I am trusting you that you... Well, yes, I know that, but red is on the outside. Okay. So this is the... Well, that's what we... I thought that's what we... Well...
Wasn't the top on the outside and the center's off? Is that what we're saying? That's what I'm asking.
Oh, the top would be the outside. Okay. See, I never pay attention to the order in the rainbow, and the only way to know the order is to either know which color has the faster speed or know which, from the rainbow. And I don't pay attention. which I should. Okay, last one on this slide. Be able to find image positions and heights produced by a lens or mirror, both graphically and through calculation. Question?
Is that the one where we're tracing?
Yes, you're going to have to do, that's what I say, you're going to have to do a ray tracing diagram. You're going to have to put, here's my lens or mirror, here's my object, and then find where the image is.
So you said that you had like a tutorial video?
Yeah. It's there in the tutorials, the same place the other tutorial videos are.
In Moodle?
On YouTube.
There's a separate tutorial section?
Yeah. Yes. Yeah, it's a different playlist in the same YouTube channel. Okay, so yes, you're going to have to do the graphical example. Question?
So what are the three names of the... Because you have the three lines to draw, right?
Oh, the three rays?
Yes.
Okay, you have the parallel ray, the focal ray, and the vertex ray. And the definitions for these, the first two come from how we define the focal point of a lens. You need to know this. If I have parallel light coming into a lens or a mirror, parallel incident rays, incident means coming in, then the place where all those rays meet, we call the focal point. Excuse me. And for a thin lens or a mirror, that focal point is the same whether the light was coming in from the left or coming in from the right. I know for a mirror that kind of doesn't make sense, but it still is correct. So when we do the parallel ray, we have the light is coming in parallel incident rays. So it reflects or refracts through the principal focal point. The principal focal point is the point where parallel rays coming from the left side, we do, by convention, we always have light coming in from the left. So where rays coming in from the left meet, that's the principal focal point. If you have a concave mirror, the principal focal point is going to be on the left of the mirror. If it's a convex mirror, the principal focal point is on the right. So let me just put these for mirrors. For parallel rays coming in like this, I got to change colors. That's ridiculous to have a red mirror and red light. The rays coming in from the left come back through that principal focal point. For the convex, it's the extrapolations that meet over there. And so this here has a negative focal length because it's on the wrong side, whereas this one here is a positive focal length. Because it's on the right side. By the right side, I mean the correct side. It's on the side that the light should go after it hits the mirror. What was that? And it's the opposite for lenses. For lenses, parallel light going like this should refract so it all comes together at one place that we call the principal focal point. And so that's a positive focal length. And it's on the right side for positive focal length. Now there is also the secondary focal point. The secondary focal point is just symmetric on the other side for a lens. For a mirror, the primary and secondary focal points are the same place. Or principal and secondary. Yeah.
So are these just going to be like word problems and then we have to draw all this?
The one that I'm talking about, the one that you're going to have to draw, yes, it'll just be a word problem. It says you have a lens or a mirror with this focal length is placed this far from an object that's this tall.
So do we need to use like a ruler for that?
Yes.
Will you have rulers?
Yes. Yes. And I will just give you graph paper from to do. The graph paper makes it easier. You'll want to use a ruler and have a scale, right? So that you can actually measure the height, because that's how I'm going to be grading it. I'm going to have a ruler and I'm going to measure the height and make sure that it's correct and make sure that your lines are drawn correctly. So one can go through and calculate and check their answer, but you still have to have the right lines drawn to get the credit. You can't just have the right answer without the lines drawn to show the construction. Right, it's to make sure you understand how to construct the image. So there is one more here that I didn't show. Whoa. Sorry, went to the next slide by accident. Like this, if I have parallel rays coming in like, those parallel rays diverge. And so my principal focal point is back there. And that's a negative focal length. And then I have the secondary focal point here would be out there.
When is the secondary focal point useful?
The secondary focal point is useful for when we get to the focal ray. So all of this was lined up with the parallel ray. The parallel ray, you start at the tip of your object, make your object so its base is on the principal axis. Your parallel ray starts at the tip of the object, goes parallel to the principal axis until it hits the lens or the mirror, and then refracts or reflects, so it goes through the principal focal point. That's the parallel ray. The focal ray starts at the tip of your object and goes to the secondary focal point and then comes out parallel. The vertex ray goes through the vertex, which is where the principal axis goes through your lens or mirror, and just goes straight. If it is a lens, if it's a mirror, it reflects back, so angle of incidence equals angle of reflection. And then where the three rays meet, or the extrapolations thereof, that's where the image is formed. So make sure you can do that. You also have the equation. The equation, most people find a lot easier. The equation, of course, 1 over the focal length equals 1 over distance image plus 1 over distance object. Works for both a lens and a mirror. Power. Sorry, I don't have room for it to fit there.
So what would we draw for? We don't have to draw all those?
You need to have at least 3 rays. And so if it is a lens, it needs to be those 3 rays. If it's a mirror, you could also use the center ray.
But you know how we have to draw like something for each one? For each problem?
Yeah, so you, for this here, your drawing would be what you're graded on. Dixon.
So on with this, there's a magnification
Yes.
equation, and that one has a negative DI.
Um,
What is that?
Yeah, just trying to find space here. Magnification is defined as the height of the image divided by the height of the object. Now, technically, this is the transverse magnification, because later on we had the angular magnification. And using our geometry, it turns out that the ratio of height image to height object is minus the distance image over the distance object. So there's where the minus sign comes in.
So if I'm just confused as when we can just where do we put in a negative on the distance image and when are
You always put a negative in if you're using this form right here. So if distance image is negative and distance object is positive, then it's going to be a positive because you'll have negative and negative.
So having a virtual or a real image, does that matter?
It does. You always have if it's a single lens or a single mirror. If it's a real image, it's always going to be inverted, which means magnification is negative, and it's always going to be real. If you have, or wait, I said if it's real, it's always going to be real, didn't I? Well, if it has a positive image distance, it will be inverted and real. If it has a negative image distance, it'll be upright and virtual. So those go together, as long as it's a single lens or a single mirror. When you have a double lens or double mirror or some combination thereof, then you have to figure it out. It could be any combination.
When they're drawing, like we were just talking about, when they're drawing like the tip of the image to the lens,
Yeah.
they always have like a slight angle change inside the lens. How do we know what that's going to be?
Okay. The slight angle change inside the lens is to try to match reality. But we are using what we call the thin lens approximation. And the thin lens approximation is that there is no thickness to your lens. So you just go straight to the center of the lens and then you bend once at the center of the lens. And if it's a mirror, draw a vertical mirror. That is, draw the mirror like this and then just put a little thing at the top and bottom to indicate which way it's curved. And then just draw your rays to that line.
This is for a lens?
Well, this here is how I draw the mirrors so I don't get confused about where to draw the lines. For lens, I draw the lens like this, but I usually put something like this down the center, and that's where I go to, and then I bend at that point.
Scroll back to the top.
Yeah,
Did you do the mirror in the tutorial, or how?
I did all of them in the tutorial. There's a different tutorial for convex mirror, concave mirror, and so on. There are 4 of them. The first one has, I think there's only 4, maybe there are 5. The first one has the introduction and the methods used and one example. And then the others have specific shapes. Okay, let's go to the other half of chapter 25. Oh wait, no, it's chapter 26. Chapter 26 is the one I broke into 2. So chapter 26, we had vision. So make sure you know what the pieces of the eye do. What's the purpose of the cornea? Yeah, it's your primary focusing element. That will focus light at your far point onto the retina, if your eye is working properly, which many of us, our eyes don't work properly. Then the iris. What's the point of the iris? Okay, it controls the aperture so it adjusts how much light comes in. As a byproduct of that, it also adjusts your depth of field. So that in bright light conditions, the depth of field is very large, so if you can focus to here, you can probably focus anywhere. In low light conditions, if you can focus to here, you can focus to here at the end because of the difference in the size of the aperture. Then what about the lens? That gives us accommodation. It allows us to adjust what we're focusing on. So I can adjust my focus from focusing on Chad to focusing on Toussaint. That's using the lens that allows me to change that. And then finally, the retina. That is what detects the light. And so the image needs to be formed on there if we're going to detect the light and see a clear picture. Now, jumping down to, I'm not sure where, I guess it's the next bullet point. In the retina, we have 2 basic types of light receptors, the rods and the cones. The cones give us color vision. The rods just give us light versus dark. The rods are much more sensitive, and so if it's a low light condition, we don't see colors, we just see bright and dark. And in old television sets, the color was pretty poorly done. The accuracy of the edges for the color in a color picture was pretty poorly done. But the accuracy of the edges for the black and white was done very carefully because the cones don't have the clarity of the rods. Of the cones, we have 3 types of cones. What are those 3 types generally called? Red, green, and blue. Now, our textbook said yellow, green, and blue instead of red, green, and blue, but that's the only time I've ever seen that in my life. So red, green, and blue is what virtually everybody uses. Those are called the primary colors of light because those are the realms where each type of cone has the most sensitivity compared to the others. Right? The red cone has its peak in yellow, hence our textbook calling it yellow. But it's the one that sees the best in red colors, and that's why we call it the red cone. The green one has its peak in green, the blue one has its peak in blue. And so when we see colors, we're simply seeing the combination of these three. Well, those give us the three primary colors of light, but if you're doing painting, you're using pigments. You're absorbing colors. And so your primary pigments, you want to absorb just one of the primary colors and reflect the other two. And so your primary pigments are one that absorbs just red, and thus it reflects green and blue. And what do green and blue together give you? Green and blue, indeed, give you cyan. One that absorbs green, and so it gives you red and blue. What are red and blue together? Magenta or purple, but not violet. And then one that absorbs blue, so it reflects red and red and green together give you yellow. And so the ones in red are the primary pigments. The ones in blue are the primary colors of light. And we call the ones above each other complementary because red and, well, green and blue gave us cyan. If you add red, then you have all three colors. And when you have all three roughly evenly mixed, we see that as white. And so red and cyan together give us white. Green and magenta together give us white. Blue and yellow together give us white. Yes?
Could you repeat what's absorbed and what's reflected?
Well, the way I aligned them, the top one is red light. The second one is below it, cyan is absorbing red light. So absorbing red light means it has the green and the blue. Right, so the next one, magenta, is absorbing green, so it's red and blue. Now, what's the difference in violet versus magenta? Violet is a very short wavelength, single wavelength would be violet. Whereas magenta is mixing red and blue together. Your brain sees them as virtually the same because the red cone has a little rise over in the violet region. So if you have violet light, it's activating the red and the blue, but not the green. So that's why your brain can't really tell the difference, but they're uniquely different. Okay, so I've covered the next two. Be able to calculate corrective lenses for myopia and hyperopia. What's the common name for myopia? Nearsightedness. Common name for hyperopia? Farsightedness. And so if you have nearsighted vision, you're able to see near things, so your problem is with the far point. And so you use lenses to correct the far point, to take an object at the ideal far point and have it make an image at your eyeball's far point. If you're correcting for hyperopia, that's farsightedness. You can see far just fine. It's a near point issue. And so you use a lens that will take an object at the ideal near point of 25 centimeters and make the image at your actual near point. Then we have two other, remember where the lens is matters here, and the images are on the same side as the object, so the images have negative distances, negative image distances. Okay, astigmatism and presbyopia. What's an astigmatism? You what? Okay, the eye is not uniform. You have basically two different focal lengths for the eyeball. And so to correct for that, you have to have a corrective lens with two different focal lengths aligned so that you're correcting for each of the two axes for the two focal lengths. What about presbyopia? What's the technical meaning of presbyopia? That's old folk vision. And so how do you correct? What's the problem with old folk vision? Presbyopia is when the lens gets hard, and so you can't accommodate as much, so your near point moves out. You were right. And so how do you accommodate for that? How do you correct for that? Bifocals or the continuous, whatever they call it, lenses. Okay, so that's our vision part. Chapter 26 also had to do with other optical instruments. So we had things like the telescope, the microscope, and the simple magnifier. Where did I put simple magnifier? Oh, here it is. So make sure you understand the purpose of a telescope, the purpose of a microscope, how we determine what the magnifications are for the microscope and telescope, what those equations are, and be able to define magnifications. Now, I told you most of the time we make our microscopes and telescopes for unaccommodated viewing because the eyepiece magnification changes just by 1 if you go from unaccommodated to fully accommodated. That's not a very big change for the eye strain that's required for fully accommodated viewing. Fully accommodated viewing is when you're focusing at the closest you can focus at your near point. But as you saw in homework, it doesn't have to be that way. You can do the magnification for other viewings as well. So you have to understand how the magnification works to be able to do these other situations. So make sure you understand our eyes only see angles basically as far as size. That's all they have for size is the angle it takes. So when we're doing magnification for our eye, it's always an angular magnification. And we have the eyepiece that does an angular magnification. We have the objective that does a transverse magnification. And the product of the eyepiece's magnification and the transverse magnification gives us the total magnification. Okay, then we have, besides the telescope, microscope, and camera, we have, and simple magnifier, we have the camera. So make sure you understand things like what the f-stop is for camera, what the exposure is, what the shutter speed is, so that you can calculate the exposures in the camera. And the camera has the correct exposure at these settings, but I want to make it have a smaller aperture. Why? Because I want greater depth of field. But what am I going to have to do the shutter speed when I, so you can do that calculation of how I would get the same exposure by changing the shutter speed and the f-stop. One thing I didn't mention here that I should have, it was right here at the top. I think it was this section. When you have two lenses, the first image, find the image, or the first lens, find the image made by the first lens. And then that simply becomes the object for the second lens. So when you do multiple lenses, it's just doing the same type of calculation twice, but it does introduce some weird things because you can have a negative object distance if you have two lenses. The example I did in class, I had the image produced by the first lens was on the right side of the second lens. So that gave me a negative object distance for the second lens. So you have to be aware of those idiosyncrasies. All right, to the final chapter, wave optics. The chapter we've just been looking at is dealing with things that only can occur if light is a wave. These can't occur if light is a particle. We will, I think it's in chapter 29, get to the particle optics. That is, things that can only happen if light is a particle. And so right now we only have half the story. We won't talk about the particle now as we review for the test because that won't be on the test. But one of the big keys for this is all of these things can only occur if light is a wave. So the things we had were single slit diffraction, double slit diffraction, the diffraction grating or reflection grating, thin film interferometer, and polarization. Now, the top four are all cases of interference. That is, you have two waves interfering with each other. The top three also had diffraction, which is bending around corners. If I have a particle model, BBs wouldn't bend around corners. And furthermore, if I have two BBs hit the same place, they're always going to add up to 2 BBs. They're never going to add up to 0 BBs. So the interference is the effect that I can have 2 waves strike the same place and add up to 0. Can't happen with particles. So make sure you understand how these things work and can do basic problems with them. Polarization is its own beast. You can't polarize a particle. Polarization has to do with the axis the electric field is oscillating on. And if you have a particle, it doesn't have an electric field that's oscillating, hence you can't polarize it. And make sure you understand, like that homework problem that had a problem, if you have a polarizer with unpolarized light, how much gets through?
50% I think.
What?
50%.
Okay, 50%. I didn't hear your words. Half of the intensity gets through. If I have polarized light and it hits a polarizer, how much gets through? Depends on the angle. It's going to be my initial intensity times cosine squared of the angle between the polarization and the polarization angle of my second polarizer. So in that homework problem, you had 2 polarizers, so you could adjust how much light gets through by changing the angle between them. The first one cut the intensity in half. The second one, you're going to have times cosine squared of the angle to the intensity. And so you can vary the intensity between 1/2 of the intensity of the sunlight down to 0 by changing the angles. Okay, that is my review. I finished 14 minutes early, so you can ask questions. I'll go with Diksha first and then with Tori. Diksha, what's your question?
On the left there, you have the single slit and the double slit and the diffraction together.
Yeah.
What is that?
Okay, single slit diffraction is light goes through a single slit. So I have something like, so I have light, and remember we had coherent light here. So the light is coming with wave fronts that are equally spaced, all the same color, all equally spaced. But then when it goes through, the light is going to, using Huygens principle, I can treat each point as if it's a new point source. And I would have light like that. And so in the end, I have some light that goes off like this, right? Because it's bending around. And when I get out to a screen that's very, very far away, we only looked at a screen that's a far distance away, I will have on the screen an intensity pattern that is most intense at the center and goes like that. And the reason for the variation in intensity is because light that goes from here to here has a different path length than light that goes, okay, I can do straight lines. The lengths of those 2 green lines are different lengths. Right? We can figure that out very quickly through geometry. And so what we do is we, using that far field approximation, we cut off here so we have effectively a 90-degree angle there and a 90-degree angle there, and an approximately 0-degree angle there. It's not truly 0, right? That wouldn't be possible. But we have a triangle that's approximately 90, 90, 0, and then the difference in the path length is this side here, which is d sine theta, where this separation here is d, and theta is the angle between my black line and the red line here. Well, the red line is broken because it's open, but another way of doing theta is to draw a line like, and theta is going to be both this angle here and the angle that we have right here. So the diffraction is the bending around the corners, right? Because light from this point can't hit that spot if it was coming in straight unless it bent. And the interference is that I had light from different places meeting at the same location. And for the single slit diffraction, we have d sine theta m is equal to m lambda m equal plus or minus 1, 2, 3, etc. for destructive. Notice m was not equal to 0 there. If m is equal to 0, it's actually constructive. For the double slit is something like this, once again, with coherent light coming through. And so now I have light coming through two slits, and if I look at a screen in the back, I will have a different kind of interference pattern, something that looks like and using the same kind of geometry. For this, you have two equations. And this is what you did in lab last week. So here we do have m equals 0. And notice that it was the same equation, but for constructive here, where it was destructive for the single slit. Why difference? Because you have a different situation. You have to go through your derivation differently. The diffraction grating is where you have a very large number of slits. So instead of a double slit, it's a million slit or 100,000 slit. And in that case, the constructive equation is still correct. But it's destructive anywhere except for where it's constructive if you have a large number of slits. So that's why we use the diffraction grating, because it's only constructive and then destructive everywhere else except for those specific angles. Does that answer your question, Diksha? Okay, Tori.
Okay, so I have a question on the practice problems.
Mm-hmm.
Chapter 23 one, number 7, it was talking about like polarization and index of refraction, and I was a little confused about that.
Okay. Let me. Number 7?
Yeah, number 7.
Okay, I'm going to take a snapshot here. It doesn't matter which one I choose for this. I'll take the picture. Got to close the warning, sorry. Like, okay, so Tori asked about this question right here. An innovative physics professor conducts laboratory exercises in the college swimming pool. Suppose that one exercise has the measurement of the degree of polarization of bouncing the laser light off a surface of glass. If the glass used has an index refraction of 1.52, at what angle of incidence will the reflected beam be perfectly polarized? Okay, the quick answer is we didn't talk about Brewster's angle.
Okay, cool. Can we just not do this problem?
Can we not do this problem?
I have other
Well,
questions I can ask you about.
It is something that is useful to know about, though. I talked about polarization on reflection and why we wear polarized sunglasses. And the Brewster's angle is the angle where you get perfect polarization. That is, the reflected light is perfectly polarized. So I have a surface like this. If light comes in, no, it will not. If light comes in at the angle that we call the Brewster angle, then you will have the light split by polarization. Theta, well, it's still going to be Brewster angle, right? Because the angle of incidence equals angle of reflection. And then we have here theta 2 And it turns out these two are 9 degrees from each other at the Brewster angle. But in this case, the light that is transmitted is going to be polarized this way, and the light that's reflected is polarized. So the electric fields are going like that. So you polarized it by reflection. And so I believe the way it works is I believe that's the equation, but we didn't talk about it, so that won't be tested. Another question? Toussaint.
What kind of questions should we expect from the last part? We asked that chapter.
Okay, from this chapter here, I expect you'll get at least one question that has to do with a type of, you'll get on average 3 questions per section. But at least one question will be about one of the types of diffraction. So like, you measure a screen this far from your grating, you measure peaks at this angle and this angle. What's the wavelength if you have this many slits per centimeter? Or if you have this wavelength, what is the slits per centimeter, something like that. Something that has to do with one of those 3 diffraction equations. And then you'll definitely have one that has to do with polarization. If you can do the stuff that was in that homework problem 4 for polarization, that pretty much is going to cover what you need to know for polarization. It's likely you'll have a 3rd one that has to do with thin films. That is, determine what conditions are necessary for constructive reflections or destructive reflections given a specific scenario. Like we had a number of homework questions doing that.
Can you explain that number? What is that exactly?
Explain what?
F number?
F number. Okay, the F number is talking about f-stops in a camera. I'm just going to make a new slide here and go to the new slide rather than trying to find space here. It's inserting a page. Sorry about delay. There we go. So, if we look at the F number is defined as F number is equal to the focal length divided by the diameter of the lens. And so, if you have, that means that your F number is equal to the focal length, which is probably 50 millimeters in most cameras, divided by the diameter of your lens. So you can find right away that the diameter is, for instance, 50 millimeters divided by 1.4 if my F number was 1.4.
Yeah, what is that? What is the function of that?
Well, the function is controlling how big the aperture is, right? You have an aperture that you can change the diameter of. So the lens itself comes with an F number, and that tells you how big the diameter of the lens is. And then you put an aperture in front that can make F numbers bigger than the F number of the lens, and that's done by making a smaller and smaller diameter for the opening in front of the lens. And, of course, the amount of light let through depends on the size of that aperture. So what you're controlling is how much light is let through. Okay, we are out of time now. So I will see you in lab mañana for the exam.